Hello everyone. Welcome to the course Introduction to Fluid Mechanics. We will be starting today's chapter with chapter 1. It's the Introduction to Fluid Mechanics. So here are the topics I will be covering in this chapter. The first is we will talk about the definition of a fluid, then some basic equations used in fluid mechanics, then we methods of analysis in fluid mechanics, and then dimensions and units used in fluid mechanics for different types of analysis. And I will introduce some basic concepts in this lecture, which are fluid as a continuum, velocity field, stress field, viscosity, and surface tension. So this is lecture is meant to go through the basics of fluid mechanics, which will be a very thorough introduction, and we will read about these concepts in detail in the upcoming lecture. So let's talk about fluid mechanics. What is fluid mechanics? You must have studied mechanics earlier, which is the study of bodies in rest or in motion. So when you combine these terms, fluid mechanics, it is the study of fluids either at rest or in motion. So what we study is the interaction of fluids with solids or other fluids in this fluid mechanics. Fluid mechanics is also known as fluid dynamics, but we know from earlier mechanics courses that dynamics is the study of bodies or fluids in motion. But here we consider the fluid at rest at where velocity is 0. So it's a special case where you see that the fluid is at rest, but we take it is in motion, but with the velocity equal 0. So you can easily call it fluid dynamics, but we will call it fluid mechanics throughout this course. So what are the applications of fluid mechanics? If you look at wind turbines or aeroplanes or water turbines or any combustion, all these are very tactical applications of fluid mechanics. But what about the daily lives? The air we breathing, the water we drink, everything you interact with in the form of fluid is an application of fluid mechanics. For example, your lungs are a very good application of fluid mechanics. You can study your lungs for the air you're taking and you take out, the way you get air into your lungs, how the pressure builds up and how you release that pressure to breathe out the air. This is how you can apply the concepts we study in this course to your daily lives. But again, as an engineering students, you will study, you will use these concepts maybe later in your careers to build an airplane, to design the fuselage for the tip of the plane that you will be working for, or the wind turbine that you are working, to study the effect of airflow through these turbines or the larger aspects, for example in a wind farm, on onshore or offshore wind farm as well. Also these water turbines, they use a lot of fluids from them, and you have to study and make them more efficient to get more energy out of them. So these are some of the applications which you can later apply to in your real life and your in jobs as well. So let's dive deep into the study of fluids. So what do you think of a fluid in general? Is mostly we think of fluid as a liquid, but fluid is not restricted to liquid solving. They can be gassy as well. So let's compare them to a solid. So whenever you put a shear stress on a solid, it start deforming. But what happens is, depending on the solid, it will either deform or it will bend and get into its the original position after you remove that shear stress. But in comparison, what happens in a solid is when a shear stress is applied, it continuously deforms. There are a very large number, or we can easily say there are infinitely large number of layers in a fluid that slide over each other, and this deformation continues until the force is removed. So how we can define a fluid in fluid is some form of matter that continuously deforms whenever there is a shear stress. So it could be of any magnitude, and there will be a continuous deformation till you are applying the shear stress. But in case of a solid, that is a different case. So you can do it both for gases and for fluid as well. So we talked about shear stress in the previous slide. What is a shear stress? So we need to understand the shear stress. Generally, we study stress as normal stress or pressure in their other engineering subjects. So what are the differences between shear stress and normal stress? Here in this slide, you can see that, or if you consider, whenever you are considering normal stress, the force is perpendicular to the surface you are putting force on. For example, here you can see the Fn force is normal to the surface, this large plane of the body where the force is normal or making a 90-degree on this with this surface. So the stress that is caused due to this force Fn will be called as normal stress. But wherever this force is parallel or tangential to this surface, for example, here you can see the Ft, it is acting along the direction of this plane. So what is happening is this is a sliding force or tangential to the surface. So in this case, the stress produced in this body is called shear stress, and the force which is creating this stress is tangential or along the surface of that body on which the stress is being produced. So this is the difference between normal stress and shear stress. Here you can see that normal stress is generally represented by this Greek letter sigma, and whose formula is Fn over dA. So what is dA? dA is the differential area over which the force N is acting. dA is a small area, or the area on which this force Fn is acting. While in comparison, we have shear stress, which is represented by this Greek letter tau. which looks like a T of inverse letter, and this is the representation of shear stress, which is equal to Ft divided by dA. dA is again the area on which is Ft, the tangential force, which is acting on this body, and the shear stress tau will get by dividing this force over the area on which it is acting. So it is very important to know the direction of the force whenever you are talking about the stresses, especially in fluid mechanics, and most of these stresses will be of shear type, and we will be using it shear stress tau to calculate this stress. And whenever we have an angular force, we will be using the component that is parallel to this surface on which this shearing stress we are considering. We will be taking the component of the force in the tangential, that is tangential to the surface. Okay, so let's talk about what are the basic equations we will use in fluid mechanics. You must have studied the conservation of mass in thermodynamics and in other physics courses. We're going to be continuing using the conservation of mass, which is very important in analysis in fluid mechanics. Then Newton's second law of motion, whenever we will be working with change in motion for there is some momentum involved, we will be using the Newton's second law of motion. Again, wherever there is angular momentum or angular motion involved, we will be using the principle of angular momentum and the law of thermodynamics, because in fluid we will be making sure that the energy is conserved, not only mass but also energy is conserved. So it will be very much used throughout this course to know whether our system obeys the first law of thermodynamics, and that's how we will analyze our systems. Then again we will use the second law of thermodynamics as well, and analysis. We use different types of analysis in fluid mechanics. Two of the main are closed system and open system. Now with closed system, you can get from the name that it's a closed system. What closed system means, you must have studied in thermodynamics as well, that it's a system where your subject or the system has a constant amount of matter in it. That means there is no flow of mass from the system to the surrounding. For example, here in this case you can see we have a cylinder, a piston cylinder assembly, where you can see the system boundary is defined by these dotted lines, and there is a gas enclosed in between this cylinder in these dotted lines, and this is a cylinder, and we have foot weight on a piston which encloses this gas. Now whenever we will be dealing with such a system, we will call it a closed system. Why? Because the gas remains in this cylinder throughout this analysis. Maybe you can decrease its volume by increasing this weight, or you can increase its rate by decreasing the weight, but the gas will remain in this cylinder. You will not let it leak out or any sort of transport of mass from this system to the surrounding. So what we will call it, we can call it closed system. And we will study more deeply in later chapters, but the main difference you can say is that there is no flow of mass from the system to the surrounding or the next system in a closed system. While in comparison, we have open system, which we also call as controlled volume, because you are thinking of a volume which is under study, and you take a certain part of that thing, that volume, and you study that volume, the interaction of fluids in form of mass flows or energy flows. But compared to the previous example we talked about, which is closed system, there the amount of gas in that cylinder was constant, and it was not leaking out, or neither any other gas was putting into that system. But in this system, what's happening is the mass can flow easily through this system. So what differentiates it is that you think of this volume only, and the content of this volume may change over the time depending on the system you are considering. For example, here in the second figure you can see here it's a pipe. It's a diversion pipe where you can see that from one side the point 1 shows enters, and from point 2 and point 3 it leaves this body, this controlled volume, and this controlled volume is represented by this dotted line, and this is our system. While the volume is constant, the content of this system are not constant, because from the inlet 1 fluid is entering, and from the inlet 3 and 2 the fluid is leaving this system. So what differentiates these two is that for closed system the volume is not important. The volume may change, but for an open system, volume is important, and the volume remains constant throughout the analysis or the consideration of this system. But the content of the controlled volume may change over time, which is opposite in the case of closed system, where the content of the and mass content of the system may change over the the mass content of the closed system doesn't change, but the volume may change. Okay, so let's talk about dimensions and units. Again, in mechanics and other physical systems, and we use different types of systems of dimensions and units according to the syllabus we are following. So we can have the SI system, or the British gravitation, or the English engineering system of units, but it's not very good to have different systems. We have to do really when we study to get a better analysis and to avoid error. So here you can see just a likely device what the SI system looks like. For the SI system, which stands for the System International, we have the basic unit of kilogram, meter, second, and Kelvin. Kilogram is the unit of mass, and the meter is the unit of length, second is the unit of time, and Kelvin is the unit of temperature. So how these are represented in form of dimension for the mass used a capital M in square brackets, and for length we use a capital L, in square brackets. For time, we use a small t, and for temperature, we use a capital T. So you got to be very careful that you do not mix the capital T and the small t. The capital T is for temperature and small t is for time. And the time will be measured in units of seconds, and temperature will be measured in units of Kelvin. In contrast to this, we have British system of units, where we have the same quantities, but we use different system of units. For example, for mass measuring, we use LBF, which stands for pound. We don't use kilograms, but we use pound in British gravitational system. And for length, we use feet, and for time, it's the same unit second, and for temperature, we use R, which is actually the unit for Fahrenheit. And the dimensions are somehow similar, but you represent the mass by a capital F and the length by capital L, time again with a small t, and temperature with a larger T. And the English engineering system, so this is somehow same to the British gravitational system, but what differentiates it here is LBF and the LBM system. LBF means pound force and LBM means pound mass. LB is the unit of weight, LBF is the unit of weight, and LBM is the unit of mass. So the LBF will be represented by F, which is simply a force because it's a gravitational force of a given body, and LBM, which is the unit of mass, or which is simply called as pound mass, is represented by a capital M, and again the length is represented by capital L, and time with a small t, and temperature with a large T. Again, we use Fahrenheit for measuring temperature. So we will be talking about some basic concepts which we happen to introduce in this lecture, which will be covered in detail in the following chapters. So the first is fluid continuum. Here you can see the dimensions and units for System International, which is simply called SI system. Here in this table, I have enlisted the basic, some four of the basic quantities, their dimension and their units. And in the last, there is a derived quantity, which is force, and its dimension and unit. For the force, for example, it's a derived quantity, which force has its own derivation, which we are not going to detail. But in terms of dimension, for System International, you can see that dimension can be shown as M, capital M, into L divided by Q square, which the unit is kg or meter per second square. This unit is also called as Newton, which is generally represented by capital N. And this is how we will be representing dimensions and units in System International. And throughout this course, I will be referring and to use the System International, and in the assignments and in the mid-example and in the final, it is highly preferable that you use the System International so that there is no confusion. and the details formula of the system international throughout this course. Well, I will be introducing some of the basic concepts in fluid mechanics. Here are some of the concepts we will be learning in detail in the later courses, but I will introduce them here in this chapter. The first is fluid continuum. So, in fluid mechanics, we take fluid for the larger scale. We don't study fluids on a very small scale, or we can say on very microscopic level. We are not dealing or with fluids on a microscopic level, but on a macroscopic level, on larger scale. For example, to introduce this continuum, we first had to understand that here in this figure, you can see we have a small particle of this fluid, and if you zoom it out very on a larger scale, you can see that, of course, human eye cannot see the internal molecules, but theoretically, if you see that when it's zoomed out and for a very larger scale, we can see that there are hundreds or tons of thousands of molecules roaming around in this fluid. So what's happening is if we check or measure the density of this fluid at a given point, it may not be constant or uniform throughout this fluid, because there may be some molecules adhering to some places, or they are continuously in motion. So maybe there may be a difference of concentration of molecules. So what happens is on the very small scale or microscopic level, this density may change of this fluid. But in fluid mechanics, we are not interested in studying the fluids on a very small scale or a microscopic scale. So what do? We study it on a larger scale, where such thing doesn't matter. For example, as I told you about the example of density, it may vary on a very small scale because of the concentration of molecules in a specific point. But in fluid mechanics, what we do, we think of this fluid as a continuous body or a continuous mass, where such things are not studied on a microscopic level. So therefore, what happens is whenever we consider a small body, it is taken to the extent that such discrepancies won't. There are no such discrepancies in this body of the fluid we take for consideration or study or our system of consideration. So in simply, what we would say that we think of it as a continuous body with constant properties. That's why it will be called as a continuum. For example, here the density you can see, which is represented by rho, can be found. Generally, we find the density by dividing the mass or over the volume of a given body. So here in this case, what we are doing is we are limiting this volume to a specific volume, which is represented by this dash, that we limit this volume, differential volume, to a specific degree or size, so that these microscopic changes doesn't matter for our calculation, and we take this state on a continuous base. So this way we can say that our fluid fits in a continuum, and we call it as a continuum. Also, on microscopic level, if we think of density, it is a function of x, y, z, and t. T here is time, because over the time the motion of molecules will change, and x, y, z are the location and the coordinates of this specific place. So what we do is we limit the size of volume to an extent that these things work better, or to take these things in a continuous matter, and this is called the fluid continuum. Then velocity plane. Similar to the continuum we just discussed, what a velocity plane is, that there are the fluid in motion. It's specific link. There are different directions of fluid motion in a given period. So it may be flowing in a given direction, but on a smaller scale there may be some amount of fluid motion. And how we define that is, for example, here you can see this velocity, which is shown as a vector, is a function of x coordinate, y coordinate, and z coordinate, and the time t. So what happened is, for a given coordinate, there may be difference of velocities on a given direction. So the overall velocity, the vector velocity, is function of these three coordinates and the time. And how we represent it? We represent it using this convention. The second equation shows on the slide. The I is used for the x coordinate, j for the y coordinate, and k for the z coordinate. So this is how we define a velocity plane in a given fluid. This is where you actually flows in different direction. Overall, it may have a single direction, or if you consider a fluid in motion, or fluid that is not in motion, on inner scale, smaller scale, there are some velocities which are evident like this. So for the velocity field, there are some more concepts we need to into, which are steady and unsteady flows. As I told you earlier, that generally we think of fluid flows in a specific direction, but that may not be the case, because our human eye is limited to seeing the fluid flows. We cannot really see the direction of flow without any visual aid. For example, even in water, to see the flow of whereas the fluid, we have to have some sort of additional thing to indicate, which I will be showing some videos in the later lecture as well. So what differentiates the steady and unsteady flows simply is that a steady flow, you can say that it's going in a unidirectional, and you have on a larger scale the fluid flows in a given direction. For example, if you turn on your tap or the water tap, the fluid flows to the or to the ground from the tap. So it's the fluid is falling from a given height of the tap to the floor where you have your floor of that room or wherever that tap is located. We can say it's a steady flow. While what is an unsteady flow? Unsteady flows are usually in very disturbed location. For example, if there's a tsunami or some kind of larger waves coming there in a sea, there the flow gets unsteady. Or, for example, when a large body moves through a fluid, it uh, behind this large body there are uh, unsteady flow. For example, if a large aeroplane moves through air behind and the train it leaves, there are very unsteady flows, which will be is discussed in streamlines on the laminar flow chapter, which is the 8th chapter, in detail. Then considering the study, we will study the fluid flows in 1D, 2D, or 3D. What this shows is the dimension. So either it could be one-dimensional, two-dimensional, or three-dimensional. Of course, in real life, every fluid flows in the three dimension. It had the x-axis, it had the y-axis, it had the z-axis. So it will always be in the three direction. But for the sake of study, we consider either it in one direction, or in two direction, or in three direction, which are simply called the dimension. So depending on the problem in hand, we will start with one dimension. We will study the flow grid in one direction, either in x-axis or z-axis or in y-axis. Then we will move to the two-directional or the two-dimensional flow grid. We will be studying both components of velocity, both in x and y or x, z, depending on the plane we are considering. And finally, we will be studying the three-dimensional growth, where we would consider all the directions, both the xy along with the z direction. And depending on this number of dimensions we are considering, the complexity of solving these equations will increase. For example, in one dimension, we will would assemble linear equation with in the second and the third dimension, we need more variables to describe the flow of the fluid. Then we have timelines, path line, and straight line. These are somehow the same concepts, but timeline in the flow of the fluid with changing time. We study the breeze over the time, how the flow changes, and we trace on their law of this fluid using markers or tracers or any type of sensors in the fluid, and this will be called the timeline, whereas path line will be where you will see the flow of grid food where it shows or the paths it takes. Straight line again is the same as the path line, and you follow the fluid through a given path or the path it takes. For example, here you can see on this automobile or this car, there are some lines of smoke which are moving around this body. So what they have done, they have put smokestacks in front of the car, which are tracing the flow of the air above this car. And you can say this is a path line. If you follow the top line, it is moving in a parabolic shape, and by the end it is getting unsteady, which we talked about earlier. The flow starts in a steady way, and as it leaves the body, it starts getting unsteady, and you can see these fault line or the straight line mixing up. Now let's talk about stress field. We started with the shear stress in fluids. When it was acted upon shear stress, it was continuously deforming. So in a fluid, there are different type of stresses present, which not like the external, but there are internal stresses as well because of the position of a fluid or the pressure inside it or the gravitational position of our fluid. So the fluid can stress can be in a given direction. As we talked about pressure and stress earlier, that pressure is generally dimensionless or the scalar quantity, whereas stress is a vector quantity with a given direction. So in a fluid there are different types of stresses. By types, I mean that these types are more of directional types, and we have generally the 6 planes for a given 3D portion, and in these 6 modes we have stresses in all those 6 planes, and we will calculate them in the upcoming lectures. But to get an idea here, you can see we have took a cube of a fluid for reference, and on the right side of this cube you can see on the x-axis we have this tau xy, tau xz, and the sigma xx. What is happening here in if you see this sigma xx, it's the stress in the xx direction, while tau xy is the plane, and it is defined by the xy xy in the xy plane where the stress is applied. Similarly, we have for y-axis and for the z-axis. So we overall get 9 different combinations for stress fields. Let's talk about viscosity. Viscosity, when we think of viscosity, we generally think of how thick a given fluid is. From thickness, we can simply understand how well it flows. If a fluid is very thick, it flows in a very slow state, or when a shearing stress is applied or any other force is applied on the fluid, it flows in a very slow rate. Then the viscosity of a given fluid is very high. So you can we can easily say that it is the analogous of elasticity in solids. The more elastic the solid is, the more flexible it is. So in viscosity of fluids, we see that a given fluid flows very well if it has low viscosity. If it has very high viscosity, then it flows very slowly or in a very tedious way. For example, water flows very well if you pour it over a surface or any object. It flows in a very smooth way, and it flows over that object very smoothly without anything, and it makes its own way. So that's water, which has low viscosity. And when we compare it to air, air has even lesser viscosity because it doesn't need much shearing stresses or forces to make it roll. In contrast, we have other fluids like honey and oil and all such very thick substances like glue or silicone, which it doesn't flow very well like water or air. So what we can say that the viscosity is very high. So whenever we will talk about viscosity, we will talk of two things. One is the shearing stress, and second is the shearing stress, and the second is the shearing stress rate or the strain rate, which we will discuss in the viscosity chapter after Woodtown. but let me introduce these things first. So what happens is, the more the shearing stress you apply, there is more shearing stress is produced in a given fluid. So again, what you can see in it here in the situation, the tau y-x, we have considered the y-x plane for in this case, in direct proportional to the shearing strength. Now, if we have a linear proportionality, to remove this proportionality, we simply remove it with a equality term and a constant. And a constant here in this mu, which is a Greek letter, represents our viscosity. So what we can say that if we rearrange this equation, we can see that mu would be tau divided by mu by dy, which is the shearing stress rate or the strain rate. So simply we can say that the mu is a ratio of shearing stress plus shearing rate produced. So whenever we have a linear relation between these two, we will say that the given fluid is Newtonian, while the non-Newtonian is opposite of this. For example, some special fluids like biological fluids like blood and toothpaste and some paints have non-Newtonian behaviors. What we mean by non-Newtonian behavior is we don't have a direct linear relation, just like the Newtonian, as I discussed in this slide. We have a different relation of shearing stress and shearing strain rate. It is not directly proportional, or we cannot simply know this proportionality with a constant term. Instead, what we use, we use a natural log and power and a constant to study the behavior of these fluids. If you work upon this equation using another account, what we get is tau would be replaced by this mu du by dy. Now mu is simply this change into du by dy to power n minus 1. So this is our shearing stress compared to shearing strain for non-Newtonian fluids. Here in this example, you can see that wherever you see straight lines, for example, this finger plastic, or the bottom one, the Newtonian one, or in the second graph, the straight line, these are Newtonian fluids where there is shearing stress and the deformation rate or the shearing strain rate is directly proportional in a linear way. The slope may be different, or three of the examples you can see that each of the three have different slopes, but still they have this linearity and linear relation among shear stress and the deformation rate. For the second fluid, you can see the dilatant and the pseudoplastic. And we don't see a linear relation. Rather, if this graph bends as it increases the shearing stress and the deformation rate along with it increases, the graph doesn't show any linear behavior. Same is the case for dilatant fluids. So what we call them, we call these two non-Newtonian fluids. And for the non-Newtonian fluids, we calculated a new property which we called as nu, or the apparent viscosity. And here you can see that we see that for Newtonian we get a straight line, which is due to the power of the power n minus 1. Every time it would be was n minus 1 would be simply n would be 1 for Newton. So what happens is simply to differentiate, you can say that whenever that we can linearly move shear stress and the deformation rate, it's a Newtonian fluid. the case is different, it would be non-Newtonian fluid. Now let's talk about surface tension as well. Surface tension, you may have heard of this term maybe in your science classes in high school. So simply, surface tension is the ability of a surface of a fluid to retain its shape. For example, if you see a drop of water or dew on a leaf of a plant, the sea will maintain its shape for a longer time. And if you shade there or be for anything, it will move in a certain way that the drop tries and to adhere to the same solid shape or the drop shape. So what was happening in the surface molecule have attraction between them, which cause them to create a force of attraction, causing that fluid to be in a certain shape, although the shape may change, but they try to adhere to each other. So, what are the consequences of this surface tension? One of them is a capillary effect. For example, in certain fluids, you see that whenever you put a capillary tube in it, what happens is called low viscosity fluid. There will be rise in the capillaries fluid in the capillary tube, whereas in case of fluids with higher viscosity, we don't have a similar case. Rather, the fluid gets depressed or decreased inside. It hasn't the same height as compared to the fluid outside the capillary. You get a height depressed than edge, which is negative in case of fluids with high viscosity, or fluids with lower viscosity. You get a positive change in the height of this fluid inside the capillaries, which is damage again. And second thing that is to be noted here is this angle that it's made by this surface with the this lining of the capillary. We call this theta, and we will study it more in the hydrostatic forces in reading the following chapters. And for now, I'm just need to get the idea of what surface tension is. So let's summarize what we studied in this chapter. We started with fluid mechanics. What fluid mechanics is? Fluid mechanics is simply the study of flow of fluids at rest or in motion. And again, fluid dynamics is another term used for fluid mechanics, which is again the interpretation of fluid mechanics. But generally, dynamics means the study of motion. But here, what happening is when studying fluid at rest, it is a special case of dynamics where the velocity is equal to zero. So we can increase fluid dynamics interchangeably with fluid mechanics. Then I discuss some of the applications of fluid mechanics, like LED bring the application and air bring the turbines, the wind turbines, and there are also those applications and the fluid mechanics have in our daily lives. But then we defined a fluid, what a fluid is. So what differentiates our fluid solid is that again, simply you can say that for a fluid is something that is not solid, but the better definition or the scientific definition would be a solid fluid is something it decays continuously when acted upon by a shearing stress. So this is a standard definition of a fluid. Then we talked about shearing stress and the normal stress. What differs these two is with shearing stress is simply the force is in the direction of the action of the plane, where the normal stress, the force is perpendicular to the action of plane or the area on which the given force is acting upon. So it's simply the difference of direction in these both. The stress, the shearing stress would always be perpendicular to the area, and the normal stress would be perpendicular to the area. Then we discussed how we usually analyze our mechanic systems. We generally categorize and them the two categories: first is open system, the second is closed system. Which you must have heard of in the thermodynamics class. The open system is simply one where there must then flow in and out of a given system. But in the closed system, the mass usually remains the same, and each work changes throughout the study or the analysis of the system. And the second difference is that in the open system, energy again can flow in and out of the system, but in closed system, energy or the volume can change, but for the opens, the volume would remain the same. Then we talked about the dimensions and the units that we will be using in this course, which are the SI units or the System International units and their dimensions. And there we will be using the kilogram and meter, second, and Kelvin, these four basic limits for our analysis, and every problem we will solve within these limits and would be standard limit. Then we talked about fluidity as a continuum, which is a very important concept, which simply tells us about the microscopic study of fluids in this course or in fluid mechanics in general, where we do not go very deep into the microscopic level or the atomic or molecular level to study the fluids. Rather, we study it on a larger scale, so that we don't have such differences. So we thought or think of this fluids of continuous or equally distributed particles in this fluid. Then we talk about velocity fields, which is simply the vector analysis of the velocity field in a fluid. Of course, when a big fluid being is not moving or is in rest, there won't be any velocity fields. But generally, for fluids that it was flowing, we would break down this into the three basic coordinate systems and to define that velocity in terms of both three its right and missing coordinates. Then we talked about stress fields. Again, we think similar to the velocity field, but there are stresses grades whenever it is flowing or whenever there's some sort of pressure, hydrostatic or then thermal pressure acting on that grid. There's a would field sort of force field in this grid, which we call as stress field, and it is defined by the plane on which we are studying the grid or the part of the grid. As shearing stress, we have we usually take shearing stress on street, so we need to ensure that we are consistent with our thing. Then we talked about viscosity, which is simply the ability of the fluid to flow easily, and the necessary viscosity that easier just to withstand flow, and the higher the viscosity, the fluid area flow very tediously, or the fluid is very thick, like honey or silicone. Then finally we talked about surface tension, which is simply the ability of the fluid in fluid circles retain its fluid's surface, the fluid's ability to retain its surface or their body of the fluid bed is in under study or to and to remain in its own share for a longer term. So with this, I complete this chapter, and see you in the next lecture. Goodbye.